When working with matrices, you first need to identify a few basics about the matrices themselves. Here, in matrix B, we can identify that it has 2 rows and 3 columns. Those are the dimensions. So you write the dimensions 2 by 3, using the X to show the word by. Then matrix M has 3 rows now and 3 columns. So our dimensions can be written 3 by 3. In order to do operations with your matrices, such as addition and subtraction, the dimensions need to be equal in order to have corresponding elements to work with. Since matrix B is missing our 3rd row, we don't have any elements to match with this last row of M. Therefore, we cannot add or subtract the matrices. If we look at matrix A and matrix D, however, they do have the same dimensions. They are each 3 by 1 matrices rather, with 3 rows and only 1 column. Therefore, we can add and subtract these elements. If I bring down matrix A and matrix D, and I want to show their addition, I'm going to identify corresponding elements inside of our matrices. So our first element is 5, and that corresponds with 6 at the top of that column. 5 plus 6 is 11. Our next match is this 6 and this 4. 6 plus 4 is 10. And our last pair, 8 plus 8 yields 16 for our final matrix, which also happens to be a 3 by 1 matrix. Now if we wanted to subtract the elements, we'd follow the same process, writing our matrices, showing our subtraction, and again we'd identify corresponding elements and subtract them accordingly. So I would take 5 minus 6 to get negative 1, 6 minus 4 to get 2, and 8 minus 8 to get 0. Now, if we want to use bigger matrices, such as C and H, the process is exactly the same. In this case, they are both 3 by 3 matrices, so we do have corresponding elements, and we can add or subtract. And I'm just going to show the addition. Again, you're going to find corresponding elements. So this 5 would match with the 1. 5 plus 1 is 6. And it's going to go on that upper left-hand corner of our new matrix. And again, 4, the corresponding element would again be in that first row, second column, which also happens to be 4. So 4 plus 4 is 8. And this negative 1 is in the same location as this 8 here in that upper right-hand corner. So negative 1 plus 8 is 7. I'll show you a couple more matches. 8 corresponds with 7. So 8 plus 7 is 15, and that element is in our second row, first column, so that's where it ends up in our final answer matrix. 7 corresponds with negative 2, so 7 plus negative 2 is 5. And the last element in that row, 6, corresponds with 6, which has an answer of 12 when we add them together. Our last 3 elements then, if we matched up our pairs, would be 16, 9, and 11. Again, the same thing can be done if you're subtracting. You just simply take 5 and subtract 1 from it instead of adding. And our last operation is called scalar multiplication. Think of it like a fancy version of the distributive property. So if I have my matrix L here, and I want to multiply it by a scalar of 2, I'd place my 2 outside of the matrix, write my matrix values inside, and then simply take the 2 and multiply it by every single element inside of this matrix. So 2 times 5 is 10. Again, 2 times 5 here, that's also 10. Now 2 times my 14 is 28. And 2 times 6 is 12. This is my final matrix then that has been multiplied by 2, or a scalar of 2. Remember, it's just a fancy version of the distributive property.